Hi everyone, I'm Miss Miller. I'm one of the Physics B teachers, and I'm here to go through some of the key findings from F1 with you, just to summarize what we learned from the experiments. So I would say that the first key finding that we really got out of these experiments was that when a constant force is applied to an object, that object will speed up if the force is in the same direction that the object is moving. So I'm going to go ahead and write that down here. And then I'm going to show you some demonstrations that really provide evidence that this is the case.
So for the first demonstration, Professor Smokey Bean is going to show you what happens when an unbalanced force is acting on an object in the same direction that the object is moving. So in this demonstration, the tilt of the track is slightly downwards, so there's a slight gravitational force acting to the right.
Alright, so here is another demonstration to show that this is the case. If you were doing this lab in school, in real school, then you would have had the opportunity to do this yourself. I have my track and my cart set up here. If I try to apply a constant force to this cart by just pushing on it ever so lightly the entire time as it moves across the track here, then let's see what happens. So pushing on it. So as I'm pushing on the cart, what you would notice if you were doing this is that the cart tries to get away from your hand as you're pushing on it. But if you maintain that same contact the whole way across the track, what we really see is that it's speeding up that entire time. So in this case, I'm providing the force to the cart. That constant strength force in this direction that it's moving causes the car to continue to speed up. Now, I have here a fan that can apply a constant strength force. My hand isn't very good at maintaining the same force the entire time, so we can use this fan to actually provide a constant force on the cart. And then I have Logger Pro set up here to actually see what the velocity versus time graph looks like for this type of interaction where the fan is always applying the same force. Alright, so I'm going to move this screen towards you so you can see what this graph looks like. So what we are observing on this velocity versus time graph is that initially the cart was completely stopped, and then I released it so that the fan was able to push on it with that constant force. And here we're seeing that the velocity goes into the negative direction, but we're moving away from a zero velocity. So moving away from a zero velocity means that we're speeding up, even though it looks like it's going down here. It's going towards larger absolute values of the velocity here. So it speeds up, speeds up, speeds up, speeds up, speeds up. Then right here, I caught it just before it hit the motion detector, and then I slowed it down really rapidly. But right here, we're seeing that constant strength force causes the cart to speed up at a constant rate. Now, one of the other key findings that came up here is that when there are no forces acting on an object, or just a balance of forces, then the object will continue to move at a constant speed. Now, this is really hard to model in the real world because there's actually always this force of friction that opposes an object's motion. On the track, it's a low friction environment, so we can get a pretty good demonstration of a constant speed with a balance of forces using this setup again. Let me just get the computer set up for Logger Pro to receive the data, and we'll see if we can get a constant speed. Alright, so I'm going to give this an initial push, and then we're going to see if it's moving at a relatively constant speed after that. Alright, bringing the computer to you. So here, we're in the negative quadrant of the velocity again. So we have a negative velocity. Here there is some little bit of noise in the data, a little bit of up and down, but it is a relatively constant velocity here until, again, my hand slowed it down before it hit the detector. So there we would see that when the cart is moving without any forces acting on it, we're neglecting friction in this case, that the cart will move at a constant speed. Okay, third key finding I'm going to show you a demonstration for. This is the finding that when an object is already moving in a specific direction and an opposing force acts on the object, meaning that there's a force going in the opposite direction that it's moving, then we're going to see that the object will slow down. So in this case, before I had the fan cart oriented where the fan was blowing this direction, providing a constant strength force this way. This time I'm going to reorient the fan so that the fan will blow this way, providing a force on the cart that's acting back towards me after I've already given it an initial push moving this direction. And we'll collect data using LoggerPro again to see what the velocity versus time graph looks like. All right, so looking at this graph, here we have that initially it's not moving. I pushed on the cart initially, so I sped it up here, but then this is the point where my hand is no longer in contact. So the cart at this point is moving this direction, and what we're seeing is that it starts to slow down here. So it's slowing down to zero velocity, and what we learned from our energy unit is that at that point where the velocity is zero, that's its turnaround point. So from here to here, it was moving towards the motion detector, slowing down. Then it came to zero just momentarily, and then turned around and started to speed up. The point that where we're looking at the object moving this direction, but having this opposing force because of the fan going this direction, is really this section where it's slowing down. Now, it's a little bit confusing to look at the graph where we're in the negative direction. So I'm going to flip this around and do it one more time to see when the object is moving away from the detector and we're looking at positive velocity. All right, so one more time now when it's moving away from the detector. So here, zero velocity initially, then I sped it up because I pushed it, and then at this point my hand's no longer in contact and we have that opposing force due to the fan. So here we see that the object is slowing down to zero velocity, and then we have that turnaround motion again right at that point. So this is evidence that indeed when we have an opposing force that the object will slow down if the force is in the opposite direction to the direction that the object is moving. All right, so there's a few other ideas that come out of the scientist reading that you'll do or have already done. I just want to summarize some of those key ideas here. So take a second to write down these key findings if you like to, and I'm going to switch to a new whiteboard so we can go through some other ideas. All right, so the next thing that I want to go through is what's called a force diagram. So first thing I'm going to do is just define a force diagram. All right, so a force diagram is a set of arrows drawn on an object that represent the magnitude and direction of the forces acting on that object. Now, these are actually vectors. We've used the word vectors before to represent velocity when we were talking in our energy unit. Remember that a vector is just a quantity that has a direction associated with it in addition to a magnitude, so how large it is. So a force can be small if you're just applying like a very small force or a small push to something, or it can be large. So we represent the magnitude with just the length of the arrow. So let's say that we have a cart that is moving to the right here. So I'm going to add to this diagram, and you often see this with force diagrams, is that there's an arrow above the object with a V on it. And that V represents the velocity. So we're using this arrow to the right to represent that the cart is already moving to the right. So it has a rightwards velocity. Then on the object itself, what you usually see is that you put like a dot just to represent that. That might be like the center of mass of this cart. And then the forces that are acting on this cart, I'm going to draw off of that dot. Let's say that this cart is being moved forward. It has a force acting on it from a fan. So we have a forward force that we're just going to label with a large F, capital F. And then the subscript to this represents where that force is coming from. So I'm going to say the subscript here is the fan, because this is a force coming from the fan. Now, let's say that this is in a higher friction environment than maybe the track here. So we do have some non-negligible friction that's opposing the direction that the fan is pushing. So we also might have a backwards force going this direction, and I'm going to label that F friction. So we have two forces, however, one of them is larger than the other. So overall, there's an overall net force acting to the right here. So sometimes you might see this, that overall we might just show that there's an F with the subscript net to represent the combination when we subtract these two forces from each other, that there's an overall net force acting to the right. So from what we have covered before, when you have a rightwards velocity and a rightwards net force, looking at this force diagram, I would be able to conclude that this object would be speeding up. You don't necessarily have to write that with your force diagram, but the point of the force diagram is to be able to look at it and conclude what would be happening to the object's motion due to the forces and the direction of motion. Let's do one other example where now we're going to have the cart still moving to the right here, but we're going to have an opposing force. So same sort of setup. I'm going to delineate these a bit. This time, the fan is acting in the opposite direction. Now, since the cart is moving to the right, friction is a force that always opposes the direction of motion. So we would also have some friction that the cart is experiencing due to all the little bumps kind of between the cart's wheels and the surface that it's rolling over. That friction is always pointing the opposite direction that it's moving. So the friction is also pointing back this way. And so now the overall combined net force is acting in the opposite direction to the direction that the cart is moving. So this would result in the object slowing down, just like we've talked about before. Now, one last example would be similar in that we have a cart moving to the right. But let's say this time that there's no fan acting on the cart and it's a frictionless surface, so friction is negligible. In this case, there's just no forces acting to the right or the left on this object, so this would be the case where the cart would move at a constant speed.